Hello, everybody. I am David Aguilar, and I would like to welcome you to the Harvard-Smithsonian Center for Astrophysics and our news conference this morning. Speaking will be Courtney Dressing, David Charbonneau, and then John Johnson, Associate Professor from Caltech, who will be commenting on the news that we're going to talk about today. Using public data from the Kepler spacecraft, we would like to thank NASA and the Kepler team. And today we are going to extend just a little bit our knowledge in our quest to try and find the first Earth-like planets in outer space. Courtney Dressing.
Thank you. Good morning. Today we are announcing that the nearest Earth-like planet is likely less than 13 light years away from the Earth. We conducted this analysis by using publicly available data from the NASA Kepler mission, which is based at NASA Ames Research Center. We began our analysis by revising the radii and the temperatures of the smallest stars that Kepler studies. These stars are called red dwarfs. During our analysis, we discovered that 60% of red dwarfs have planets smaller than Neptune. That's a remarkably large number. We also learned that 6% of red dwarfs have Earth-like planets. By Earth-like, we mean planets that are roughly the same size as the Earth, that receive roughly the same amount of light from their host star that the Earth receives from the Sun. The reason why we decided to focus on these small red dwarfs is that, contrary to what you might have learned in school, the Sun is not a typical star. In fact, most stars are red dwarfs. Here I'm showing what a typical night sky might look like from a dark place on the Earth. You can see lots of stars that are kind of like the Sun. These stars are kind of hot and big. But if we add in all of the red dwarfs that are actually up there but are too faint for us to see, you'll realize that 75% of the stars in the solar neighborhood are actually red dwarfs. This means that if we want to understand how many Earth-sized planets there are in the galaxy, it's very important to study the fraction of red dwarfs that host small planets. Another advantage of studying these small stars is that these stars are much cooler and smaller, and they emit less light. That means that any planets that are within the so-called habitable zone, which is the Goldilocks region in which a planet receives the right amount of light from its star in order to have liquid water on the surface, would orbit much closer to the star. Here's where that Goldilocks zone is for planets orbiting stars like the Sun. If you look at this figure here, we have a Sun-like star in the center, and then a green ring marking the region in which a planet receives enough light to have liquid water on the surface. If a planet orbits closer to the star than this green ring, it is too hot to have liquid water on the surface. It's kind of like Mercury. If it orbits outside the outer boundary of this green ring, it's too cold to have liquid water, something like Mars. Here, the white dashed line indicates where the Earth is in its orbit. It's near the inner edge of the habitable zone. If I now show you what the habitable zone looks like around a red dwarf, you can see that it's much closer to the star. That means that any planets in the habitable zone of red dwarfs have much shorter years. So it's easier for astronomers like us to find Earth-sized planets in the habitable zone of red dwarfs than it is to find Earth-sized planets in the habitable zone of Sun-like stars. In this study, we analyzed approximately 4,000 red dwarfs studied by the NASA Kepler mission. And those stars host 95 planet candidates. Here I'm showing you the size of the planet on the left side of the plot versus the light received by the planet on the bottom of the plot. At the top of the plot, I'm showing the amount of light received by 4 planets in our solar system. On the very left, we have Mars, which receives roughly half the light that the Earth receives from the Sun. And on the far right, we have Mercury, which receives about 7 times the light that the Earth receives from the Sun. Looking at this figure, you can see that there are 95 planet candidates orbiting the Kepler red dwarfs. Because we know how well we've searched each of these stars, we can figure out how many planets we would have been able to detect in the sample. And by comparing the number of stars around which we would have been able to detect a planet to the number of planets we found, we can estimate the fraction of stars that host planets. We find that at least 60% of red dwarfs host planets smaller than Neptune. That's an exciting result. We also find that if we concentrate on that Goldilocks zone, that there are 3 planet candidates within the habitable zone, and another 5 planet candidates that orbit near the habitable zone. Using those 3 candidates and the probabilities that all of those candidates are within the habitable zone, we're able to estimate the fraction of red dwarfs that host Earth-like planets. We find that 6% of red dwarfs host Earth-like planets. Now, the red dwarfs studied by Kepler are far away. But because those red dwarfs are like the red dwarfs that are in our solar neighborhood, we're able to use this estimate that 6% of red dwarfs host Earth-like planets in order to figure out how far away from the Earth we would need to look in order to find an Earth-like planet orbiting a red dwarf. We find that the answer to the question, how far away is an Earth-like planet, is actually quite close. The nearest Earth-like planet is expected to be about 13 light years away. To put things in perspective, if we scale the Milky Way galaxy down to the size of the United States, we find that the nearest Earth-like planet isn't across the country. It's not even across the state. In fact, if we all were to take a field trip to New York City and we stood on one side of Central Park, we'd find that the nearest Earth-like planet was just across the park. So the nearest Earth-like planet is simply a stroll across the park away. In summary, we learned today that most stars are red dwarfs. So if you'd like to know the answer to how many planets there are in the galaxy, it's very important to figure out how many red dwarfs host planets. We learned that at least 60% of red dwarfs host planets smaller than Neptune, and that 6% of red dwarfs host Earth-like planets. Again, those are planets that are roughly the size of Earth, that receive roughly the same amount of light from their host star that the Earth receives from the Sun. If we then compare the 6% occurrence rate to the number of red dwarfs in the solar neighborhood, which as you saw in the image of the night sky is incredibly high, we learn that the nearest Earth-like planet is probably 13 light years away. Astronomically speaking, that's just a stroll across the park.
Well, great. Okay, so what I would, I think, like to add to this conversation is, up until this point, we've been really talking about planets that are Earth-like, and they are in two important respects. They are the same size as the Earth, that's very important, and they are the same temperature as the Earth, and that's also very important if they are, for example, to have liquid water. However, these planets that we're talking about are very different in many respects compared to our own Earth. And much of that difference owes to the different kinds of stars that they orbit. So importantly, you've heard that most stars in the galaxy are these red dwarf stars. And I think it's important to look at that for a moment and see how different these stars are. Here I'm showing the relative size of a star like the Sun compared to one of these typical red dwarf stars. These red dwarf stars are about 1/4 the size of the Sun. They're about 1/4 the mass of the Sun. Importantly, they only put out a tiny fraction of the energy that the Sun emits. So if you picture the Sun as a 1,000-watt light bulb, these stars would be Christmas tree lights. They would emit 1 or 2 watts of energy. Okay, so they're a very humble amount of energy coming out, and as a result, planets that are just the right distance to be the same temperature as the Earth have to be tucked in close to these stars. But of course, they are incredibly common stars. All right, now in what other ways do these red dwarf stars differ, and how might that affect the planets that orbit them? I think most importantly, red dwarfs are active. And what I mean by active are two things. Red dwarfs are incredibly spotty. So they have large spots that block some of the light trying to leave the star. And as the star rotates, the amount of light that strikes the planet would actually vary over the course of days or months by several percent. If that were to happen on the Earth, it would cause havoc. But these planets that orbit these M-dwarfs, these red dwarfs, are going to have to deal with this. And I'm showing the light curve, one of the light curves that was produced by the NASA Kepler mission, showing that variability, where we can see the brightness of the star changing. And I want to point out how good the pipeline is that's able to find those small planets tucked in. In fact, on top of this very spotty star, these little red points show the signal of a planet orbiting this very spotty star. These red dwarfs are active in another sense, which is that they emit a very large amount of energy in the ultraviolet. And so this is a very ionizing radiation. It would have enormous consequences for the planet's atmosphere. Very early on, when these red dwarfs are young, they emit a lot of this high-energy radiation that might remove the atmosphere, so that might have devastating consequences in terms of the habitability. Also, ultraviolet radiation might sterilize life on the surface, or it might have other interesting effects for the evolution of life. And so I think it's very fascinating to think about whether, in fact, these planets could be inhabited. Another important thing to know about planets that might orbit these red dwarfs is, as we talked about, because the distance at which the planet has to be is tucked in so close, the planet might be tidally locked, by which we mean it's so close to the star that it would have been locked into a configuration where it always presents the same face to the star. And so as a result, there are some places on the planet that are in perpetual daylight. There are some places on the planet that are in perpetual darkness. And so, for example, there may be parts of the planet that are very hot and some that are very cold, and also an exciting terminator region. The atmospheric dynamics would be completely different than we're used to here on the Earth, where we don't have that situation. But an analogous situation in terms of understanding what it means to be tidally locked, of course, is if you gaze up at the moon. The moon always presents the same face to the Earth. The third way in which these red dwarfs are very different, and I think it's very exciting to think about, is that they are incredibly long-lived. They never show their age. As you all know, the Sun and the Earth were formed roughly 4.5 billion years ago, and the Earth has roughly 1 billion more years of habitability before the Sun brightens a little bit due to the changes in the nuclear burning in the core of the Sun, and the Earth will no longer be habitable. Okay? So there'll be a runaway greenhouse effect. And so planets like the Earth orbiting stars like the Sun are habitable for only 5 or 6 billion years. This is not the case for these red dwarfs. Red dwarf stars burn their nuclear fuel very slowly. They don't evolve significantly over their lifetimes. And so what is so exciting, I think, about this announcement today is that it raises the real possibility of conducting a survey of the solar neighborhood, nearby stars, and finding planets that are like the Earth in terms of their size and temperature, but are actually much, much older, and actually seeing what that consequence would be for seeing a 10 or 11 billion year old Earth-like planet. Okay, so those are the three important ways in which these red dwarf stars are quite different, and as a result, planets that orbit them might be very different than the Earth. I also want to briefly just really look ahead and think about what we are going to do now that we know how common these planets are, and we know that they are, in fact, relatively common. For me, I think one of the most exciting things we might consider doing is studying the atmospheres of these planets. And so we want to identify very nearby examples. So the Kepler mission has told us, through Courtney's analysis, that these planets are very common, but those stars that Kepler studied are very distant. We do not know the very closest Earth-like planets, but we now know that they're out there. So we need to design experiments to actually go and find the very closest ones. And when we find examples that pass in front of their star or behind the star, we can study the atmosphere. And there are two very important observatories that we are currently working towards that are going to allow us to do that. The first is the NASA James Webb Space Telescope. This is the successor to the Hubble and Spitzer space telescopes. It's going to be able to detect infrared light, and it's going to be in a very stable environment in space. And this might allow us to actually see the thermal emission from these very nearby planets and directly study some of their properties and really see how Earth-like they are. When the planets pass in front of the star, we get a special opportunity, which is that some of the light from the star will pass through the outer parts of the planetary atmosphere, and imprinted on that will be the chemical absorption features of whatever atoms or molecules are present. We can't do these studies for stars like the Sun because the Sun is so big that that signal is tiny and no conceivable telescope would be able to measure it. However, now that we know that the most common kind of star in the galaxy, which is physically small, has a relatively high rate of occurrence of these Earth-like planets, because the star is small, we now have reduced the contrast of the star, and we can actually hope to study the atmosphere of the planet directly. And there's an observatory that here at the Harvard-Smithsonian Center for Astrophysics we are working with our partners to build, which is the Giant Magellan Telescope. So this will be much larger than any current observatory in existence, and it will be able to gather so much light that during that very brief interval of only 1 or 2 hours when these nearby planets that we hope to find pass in front of their stars, we could hope to sense the atmosphere and the atoms or molecules, maybe even look for the chemical signatures of life, such as oxygen. Okay, so for me, the consequences looking ahead are enormous. I think what we need to work towards now is thinking about what kind of an experiment. We really need some ability to go and find the very closest eclipsing nearby Earth-like planets orbiting these M dwarfs. And so that's certainly something I'm going to be working towards starting tomorrow. All right, I think I'll hand things over to John Johnson.
Well, thank you. These are truly exciting times. And this announcement today highlights just how quickly this field of extrasolar planets is moving. And when I started studying planets back in 2000, making me one of the old-timers, there were 33 known planets, and all of these planets were gas giant planets. The smallest of them was maybe about the size of Saturn. We now know, instead of 33 planets, we know of 3,300 planets when you include all of the candidates that are in the Kepler sample. So our knowledge of the diversity of planetary systems throughout the galaxy has increased 100-fold in just the past decade. And so with that comes greater perspective for our own solar system. And it kind of gives us a grander galactic context of how our own solar system fits in. And this result shows that our solar system, with its yellow G-type star in the center, is quite rare. And it's quite remarkable that the vast majority of habitable planets throughout the galaxy are likely around these red dwarf stars. Also, we're finding that small planets are far more common throughout the galaxy than large planets. So the gas giant planets that we've been studying for the past decade, or decade and a half, are literally just the tip of the iceberg, whereas we would have to search hundreds of stars to hope to find one gas giant planet. We now know there's approximately one planet per star throughout the galaxy, and the majority of those are found around the red dwarfs. So this is also telling us where to find additional planets. And we now know also that the planets are so common that we're now moving from this era of planet hunting. We used to call us planet hunters. I believe the next step is to reach out and gather up the planets that the Kepler mission, the census conducted by the Kepler mission, are showing us that are right next door. And so this result that the nearest habitable zone Earth-like planet is only 13 light years away is extraordinarily exciting. It's right within reach. And what we need to do is to take the next step in designing the next generation of instruments that will allow us to gather these small planets from the sky, study their details in their properties in detail, and provide us with an understanding of how Earth-sized planets form. It will give us that grander galactic context, and it puts us hot on the trail of finding life elsewhere in the galaxy. Because keep in mind, all of these planets that we now know are out there, these are physical locations, places throughout the galaxy where life could have emerged. And way down the line, the science fiction part of my heart and soul starts thinking about the possibility of traveling to one of these planets one day and perhaps taking our first step out into an alien world. Before this was pure science fiction, and now I think the conversation is actually starting in earnest about thinking about these other places throughout the galaxy.
Courtney, David, John, thank you. We would like to go now to questions from the media. If you have questions, please raise your arm. We will pass the microphone to you, and then we will go to our media questions online.
Good morning. Camille Carlisle from Sky and Telescope. I'm wondering about a bigger picture reaction to this. There was recently a study that looked at super-Earths and whether they would be able to lose their hydrogen proto-atmospheres, and it looks like they might not be. There might not be enough UV radiation. While you were thankfully quite careful about your definition of what Earth-like is how likely do you think it is that these Earth-like planets aren't mini Neptunes? Would they actually be able to have a habitable atmosphere, or will they just not because of their stars?
Great question. The planets we consider as Earth-like are actually much smaller than the mini Neptunes and super-Earths discussed in that study. And likely these planets are rocky. And we don't know the exact contents of their atmosphere. Maybe they have an atmosphere that's mostly methane that supports an entirely different type of life. But we're fairly confident they are rocky and not balls of gas.
Do you think that the radiation from the M dwarfs will be enough that it can blow off the nebula gathered gas and produce this rocky planet with a smaller atmosphere?
Well, if I can just jump in. So the most important thing in terms of understanding whether these actual planets and candidates really are mini Neptunes is their diameter. right? That's the thing that actually, because if they have this large envelope of hydrogen, they're physically larger. And I really want to emphasize that Courtney in her study was extremely careful to pick only the very small planets that truly are 1 Earth radius. Sometimes you'll see discussions about super-Earths and so on, and I've participated in that, in which it's very generously defined what is a super-Earth. But here we really are talking about Earth size. And so we really think it's very unlikely that these objects have hydrogen envelopes. If they did, they would not be as small as they were observed them to be. In terms of thinking about what does happen to their atmospheres, whether the atmospheres are hydrogen or not, yes, I think there have been some tremendous studies about the ultraviolet emission that these M dwarfs have, particularly when they're young, whether that would remove the primordial atmosphere. Even without that, we expect many of these planets to be warm enough that actually, given their age, they would simply lose a lot of hydrogen. Hydrogen being such a low mass particle, it actually will naturally make its way away from the Earth and out into space as well. So we do think it's unlikely, but certainly the field of exoplanets has been a story of surprises. So I think what we need to do is actually go and study the atmospheres.
Another question? Rick Feinberg.
Hi, this is Rick Feinberg from the American Astronomical Society. I have 2 questions. The first question, very quick, is are the 3 planets that you've identified in the habitable zones around M dwarfs with Kepler, are those confirmed planets, or are those still in the category of planet candidates?
Those are planet candidates.
Are they, is the system, does it have the right characteristics that you will be able to follow it up and actually confirm them?
So these planets are all small enough that we'll have to go for the validation route, which has been previously used for other small planets. And what we would do in this case, and what we plan to do, is to try to rule out all of the other things that could cause the signal. So we'll look for evidence that maybe there are 2 stars in the fields and they pass in front of each other and cause a dip in the light curve. And we'll also look for evidence that maybe the signal is due to a planet, but it's due to a Jupiter-sized planet crossing in front of a different star. And we're planning to investigate those possibilities and do our best to say that either this is a planet or it is a false positive. And the nice thing about our analysis is that it's robust enough that even if one of those planets is actually a false positive, we have enough planet candidates either in the habitable zone or close to the habitable zone. So if we add up the probability that all of those are within the habitable zone, our result is still 6%, even if one of them is a false positive.
I'd like to add to that is that, it's a testament to the high photometric precision of the Kepler telescope. A lot of the sample of planet candidates is a really high fidelity sample, and the false positive rate should be quite small. Less than 10% on average. And in a separate analysis, my team has done a star-by-star analysis of this. And by knowing the physical properties of the star, which is what Courtney Dressing is now providing us, we can rule out a lot of those false positive scenarios. Another really interesting benefit for some of the smaller, closest M dwarfs in that sample is that they're so nearby that they move across the sky by virtue of what's called their proper motion. And so you can actually look back at photographic plates, some of them taken here.
Yes.
And
Actually,
you can,
they're only 50 feet away.
exactly, yeah, right across the hallway there.
Across the park.
Yeah, and and you can actually take a peek from a plate in 1950 and just take a peek at what was underneath the star right now. You can so basically go back in time and verify that there's not another star that's hiding there that could mimic the signal of that planet. So I believe that this, particularly for the M dwarfs, this is a very high fidelity sample. And what remains is to do the star-by-star analysis to back that up.
If I may, with my second question, how does this Kepler result, in terms of percentages of planets around M dwarfs, square with what you're finding or have found so far with the M-Earth or MERTH project, which is also looking for Earth-like planets around M dwarfs? But I think from the ground, if I'm not mistaken.
Yes.
So maybe I should answer
That
that.
makes sense.
I'm the principal investigator of the MERTH project. So MERTH is a ground-based survey using an array of 8 relatively small telescopes. These are 16-inch telescopes to survey nearby M dwarfs. MERTH is very much, going to pick up on these rates of occurrence and try to go and find the closest examples. That's why it exists. But it does not have the ability to find truly Earth-like planets, 1 Earth radius. So MERTH is sensitive only to planets that are twice the size of the Earth or bigger. Those almost certainly are sub-Neptunes or whatever you'd like to call them. They would have these large envelopes. And so I think we are going to need something else, possibly from space, to really go and find the very closest, truly Earth-like analogs. In terms of squaring up what we do know, we can compare the rate of occurrence of these relatively, these medium-sized, Neptunes and sub-Neptunes with Kepler, and those match up very well. And that was a study done by Zach Berta, who's a graduate student working here on MERTH. MERTH is perfectly consistent with what Courtney has derived for the rate of occurrence of these Neptunes and sub-Neptunes from Kepler.
Hi, I'm Kate Becker with NOVA, and I am wondering, you'd mentioned kind of some of the negative consequences that the ionizing UV radiation might have for the evolution of life on one of these planets. Could you go into a little bit more depth about those implications and perhaps mention, are there any positives?
Well, I should be clear here that I'm an astronomer, and my hope is to become a biologist by the end of my career. And I'm sincere in that. But I do not speak with any authority about the consequences of ionizing radiation. But certainly, I imagine that the process of mutation, which ultimately drives a lot of the changes that have happened in terms of the organisms on the Earth over time, has relied in part on ionizing radiation, like this ultraviolet radiation. I do know a little bit more about atmospheres, and there have been some wonderful studies, not by myself, in terms of studying, the energy deposition. So the point is, you have these very high energy light, which you can absorb by the atmosphere and physically blow it off. And so what we really need to know to answer your question is, we do not know how much ultraviolet and high energy radiation these nearby red dwarfs emitted during the very first 10 or 20 million years of their life, because that's when all the action happens. We now know that many of them are quiescent, so a lot of them emit very little now, and so the atmosphere, if it survived that initial period, would continue to survive. Some of them remain active throughout their lifetimes. But there's very little known about the ultraviolet radiation from the very youngest M dwarfs. But our hints are that they are very active, and that would be enough to remove a substantial portion of the atmosphere.
One of the other negative consequences that Dave mentioned was the possibility of tidal locking. We don't know what that will do. We know that it will make things very interesting on the surface. It could mess up the conditions for life. It may not. But it's also important to note that that's not a necessary end state. A lot of these M dwarfs have multiple planets around them. And those interactions among those planets can drive eccentricities. And once you have an eccentric orbit, like Mercury in our own solar system, the planet does not necessarily end up in a tidally locked state. And so that's one way of getting around the issues of tidal locking. But I think one other important thing to point out is that we don't quite understand the conditions of habitability on this planet. We know that there are many. The list is 20, 30 different conditions perhaps. Is it important to have a moon? Is it important to have a Jupiter-sized planet, or does that actually mess things up by tossing things inward? Do we need plate tectonics? And so what this discovery does, I believe, is it drives forward those studies of the conditions for habitability on our planet, and provides us with a target to aim for. Now we need to, once we identify what those conditions are here, we now know that we have to apply them to small planets around red dwarfs.
And I think what we're all so excited about is, each of those things you list, we can test. I can think of an experiment that would allow us to go and look for moons. I can think of an experiment that would allow us to make sure whether or not these nearby planets we hope to find have a Jupiter at some larger orbit. So as we, now that we know that there are going to be Earth-like planets very nearby, so that our upcoming and even current telescopes can really get at them and study them. We don't have to look too far afield. We can actually start to tick down that list of habitability conditions. And then when we actually get to the point of studying the atmosphere and seeing whether they are in fact inhabited, I think then you'll really see this explode.
How were you able to reduce the star radii and therefore the planet radii? Because reduced them quite a bit.
Right. Well, the stars and planets have always been the same radius. We just didn't know how big they were before. Yes. Yes. So what we did is we used models that are more appropriate for these small red stars. And initially, when the Kepler team was developing their target list, they needed to do a remarkable task of figuring out how big and how hot all of the stars in the Kepler field were. So a team led by Tim Brown and Dave Latham actually went out and got images of all of these stars in different colors. And then they used models that work very, very well to figure out the temperatures and the radii of stars like the sun. But those models overpredict the radii and the temperatures of these smaller red dwarfs. So in our analysis, we update their catalog of stellar properties by matching the observed colors of these red dwarfs to the colors we would expect from the Dartmouth stellar evolutionary models.
And so it's worth noting that the vast majority of Kepler targets are sun-like stars, and that great quest of figuring out whether there are Earth-like planets around sun-like stars, that lies ahead of us, and that's something that any of us associated with the Kepler mission are very excited about. But I think what Courtney really seized on was that there was already plenty of information about these red dwarfs, and they're actually the most common. They're not our star, but they are the most common in the galaxy. And then by carefully considering the astrophysics of the stars and the planets, learning 6% of them are going to have an Earth-like planet.
And I think it's also interesting to note that the study of exoplanets is really driven by our understanding of stellar astrophysics. Every detection technique that has been successful in finding planets relies on knowing the properties of the stars in order to know the properties of the planets. And so Courtney Dressing, just like any good exoplanetary scientist, is really to become an expert in stellar astrophysics. And that was what actually unlocked this discovery about planets, was unlocking the physical properties of the stars in the Kepler field.
Hi, Rick Feinberg again. The press release that went out this morning mentioned a paper in the Astrophysical Journal, and I'm wondering, is the occasion of this announcement the acceptance of that paper or the publication of that paper, and will that paper be available online?
The paper will be available online, and we anticipate that it will be accepted soon.
So we've responded to all the referees' comments, and so we actually anticipate it'll be accepted in a day or two. But I don't want to prejudge that. But we definitely will make it available, and it should be on our website.
Yes.
Christine, do we have some questions online?
Yes, we do. The first question online comes from Marcia Dunn from the Associated Press. And she asks, could you please offer a snapshot of this planet 13 light years away? I realize this planet is Earth size, give or take. Is there any way to tell whether it is older than Earth and by how much?
So we actually don't know which planet this is. We've discovered that there should be a planet within 13 light years, but we need other missions to actually find that planet. Given that many red dwarfs live for a very, very long time, longer than the age of the Milky Way galaxy and the universe, we think that this planet may be as old as the Earth. It might be a little bit older, it might be younger. And I really look forward to finding that first planet or seeing someone else discover that first planet and learning more about its properties.
Okay, the next question online comes from Pete Spots with the Christian Science Monitor. And he asks, can you review the reasons why a red dwarf's activity and the tidal locking may not represent the large hurdles to life as some might have thought?
Well, we've discussed some of that, but I will add a little bit to the discussion. One is that I think if you go back and you read the research articles about why these red dwarfs were kind of dismissed as being potential sites for inhabited Earth-like planets, it's fascinating. I think that there's all these carefully constructed arguments as to why life couldn't exist on a planet orbiting a red dwarf. I think that with hindsight, we see that as a myopia for having grown up around a sun-like star. We had convinced ourselves that, obviously, since we orbited a star like the sun, that had to be the way things were throughout the galaxy. And if there was one message from the last 15 years of exoplanet discoveries, it is that there's no guarantee that our solar system is a commonplace, that there's enormous diversity of architectures, and that basically anytime we have the sensitivity to find planets around a different kind of star, we find planets. Okay? So let me give you another reason why the tidal locking may not be an issue. So John Johnson described very clearly that actually there's no guarantee that just because the planet is close, it's tidally locked. Even if it is, provided that the planet has a reasonably thick ocean or a thick atmosphere, that will provide a mechanism to redistribute the energy that falls on the day side over to the night side. So, assuming that the night side, which is in perpetual darkness if it is tidally locked, is at absolute zero, and that the hot side is very hot, is at odds with our experience here, even in Cambridge, Massachusetts. When the sun sets, it does not drop to absolute zero. And that's because we have an atmosphere, and that's because there's a thermal inertia associated with the ground and with the ocean. And so the point is that any reasonably thick ocean or atmosphere will keep all the parts of this planet reasonably toasty.
Next question comes from Elizabeth Howell for Space.com. She asks, when Dr. Charbonneau said that red dwarf stars live forever, does he mean 60 billion years as indicated in the diagram? If not, how long and why?
I mean, almost forever. So we know that the universe is roughly 14 billion years old, and the any red dwarf that's been born at any point in the history of the universe has never gotten to the point where it's begun to show its age. So obviously the ones that are born only 5 billion years ago are 5 billion years old, and they may live for another 10 or 20 or 100 billion years into the future. But my point here is that the universe is 14 billion years old. There were stars forming perhaps 12 billion years ago. We do find examples of those stars in our neighborhoods. There are neighboring stars that are much older than us. And so they may have, if they have Earth-like planets, those planets have been in existence for a very long time. And so all of the interesting processes that are happening here on the Earth that cause a planet and its life to evolve would have had a much, much longer time scale. But it is worth pointing out that, yes, the very low mass stars, the very low mass red dwarfs, they can live much longer than 60 billion years. At that point, it's just a theoretical calculation, because obviously the universe has not been in existence long enough to see how long they truly can live. But they can live hundreds of billions of years.
We've never seen a dead one.
That's right. The short answer is we've never seen a dead one.
And a follow-up question from Elizabeth Howell. You kind of covered it already. How old could the oldest Earth-like planets be, assuming that they form as soon as possible after the beginning of the universe around red dwarfs?
You want to answer that?
I think you said 12 billion years, which is reasonable.
So a very active field of study in astrophysics is to figure out how early stars formed, and did those first stars, could they have formed planets? We think that it really took later generations of stars, because this first generation of stars had to go and make the things out of which planets are made. They had to go and make the heavier elements. But I think it's perfectly reasonable to expect there to be stars that might have planets that could be at least 12 billion years old. Mm-hmm.
We also have several questions from Alan Boyle at MSNBC. The first question, the news release mentions that 3 out of 95 planetary candidates were Earth-sized with habitable temperatures. That's less than 6%, but are you also factoring in expected Earth-sized candidates that have not yet been detected?
So in our analysis, we compare the number of planets we found and the number of planets that could be orbiting the star but wouldn't be aligned for us to see them. So with the transiting survey, you only detect the planet if it crosses in front of the planet as seen by Kepler. So we can correct for the odds that a planet at a given distance from the star will be properly aligned. And we use that correction in order to figure out how many planets those 3 planets actually represent. And then in order to figure out the occurrence rate, we don't compare the 3 planets to the 95 planets. We actually compare the 2 planets that are in the habitable zone and Earth-sized, and the 1 planet that's slightly bigger, and also the planets that are slightly outside the habitable zone, and figure out the probability that each of those are Earth-sized and within the habitable zone. We then look at all of the red dwarfs in the Kepler sample and figure out, could we have seen an Earth-sized planet getting the same amount of light from its star as the Earth orbiting that particular star, given the number of days that Kepler has observed that planet and the number of transits Kepler would have seen.
Second question from Alan Boyle. How did you arrive at the 13 light-year figure?
So for the 13 light-year figure, we estimated that 6% of red dwarfs host Earth-like planets. And we used data from another survey that measured the types of stars within 30 light-years from the sun. And they have 248 red dwarfs within 30 light-years from the sun. So we compute the density of red dwarfs in space and figure out how far out from the Earth we need to go in order to find one of those Earth-like planets that should be, hopefully, within 13 light years.
Thank you. Final question from Alan Boyle. Is the key to this research the finding that red dwarfs are cooler and fainter than previously thought?
No. So in this research, we use models of red dwarfs, which have already been determined using observations of red dwarfs, and those models accurately reflect the fact that red dwarfs are cool and small. When the Kepler team established their catalog of stellar properties, they added a note saying, we know we've overestimated the radii and the temperatures of the red dwarfs, so please use caution in using these numbers. So we took that guidance and we decided to use those models of red dwarf stars in order to update the values in the Kepler target list. And as Professor Charbonneau mentioned, most of Kepler's target stars are stars like the Sun, and the values they provided work very well for those stars.
Thank you.
And maybe just to add in, so I would say, yeah, the keys to this research are to very carefully understand the properties of the stars in the Kepler sample, to re-examine all of the planetary candidates and refit those light curves, which Courtney did, and then to very carefully understand the statistics. So basically to figure out, for on a star-by-star basis, could we have found this kind of planet? Could we have found this kind of planet? Some stars were too noisy, and we had to factor that into account. And then also to take into account the geometry. So we know when a star is at a certain distance when a planet is at a certain distance from its star, we can figure out the fraction of those that eclipse and the fraction that are up here from your point of view, or up here from your point of view, that don't eclipse. That's just pure geometry. Those four things put together, that is the result here today. This is giving the 6% number.
We have a question from another side of the room.
Hi, Al Powell from the Harvard News Office. How close is the closest red dwarf? And is that 13 light-year figure the likeliest candidate? And how close is the most possible, or the closest possible candidate?
Well, the closest one is Proxima Centauri, which was in the news recently because Alpha Centauri B has a small planet, which is not in the habitable zone. It's much closer to the star. And the 13 light-year figure is the most probable distance. And if we want to give our 95% confidence limit on the distance to the nearest Earth-like planet, then that would be a larger figure of 21 light years.
But it bears noting that all of those, any astronomer will tell you that that's as close as things get. These are incredibly close distances to stars. Talking about whether it's 13 light years or 20 light years is incredibly close compared to the scale of the galaxy, as Courtney showed.
With that, I would like to conclude our news conference. I'd like to thank Courtney Dressing, David Charbonneau, John Johnson on behalf of the Harvard-Smithsonian Center for Astrophysics, and I'll leave you with this last thought. Isaac Asimov once said, "Earth is the only planet we know of that has life on it. So far." Thank you.